So the next, there's another example that I would like to do, but it's very similar to what I've just done, so I won't do it. But rather than that, we will go into the next topic. Okay, we are still under buckling. So the next topic that we're going to look at is what we call. Let me draw a line across so that you know that this is the end of centric buckling. Okay. So the next thing that we're going to look at is what we call eccentric buckling. Okay. So let's what do we mean by eccentric buckling? So I'm going to get you to recall, okay, regarding the term eccentric bending. Okay. I want you to, I'm going to, so if we have eccentric bending, okay, our structure will usually look like this. Okay, so this is our structure. So this is point A, and over here, this is point C, and point C is the point of interest. And if I were to sketch a line, I'll sketch a line over here. Okay, and then another line. Okay, one. Let me get rid. Oh, no. Sorry, my bad. Shouldn't have done that. And then another one. The distance between the two green line, okay, this distance over here is E. Point C is the point of interest. So this is our centroid. Okay. So the green line where I drew, there's a force P. Okay. So this P, right, being a certain distance away from C, right, is what we call E. Okay. So there is a moment acting in this direction, right? So moment at point A is equal to what? E times E, right? So based on Newton's third law, right, at point C, there has to be another reaction, which is P, right? That will take care of the vertical forces. So if this is X, this is Y, this is rotation about Z. And then at point C, there has to be a counter moment. So the counter moment, this is moment at point C. Okay. So that is why at point C, okay, so the normal stress at point C, or the normal stress in the y direction at point C, is equal to P divided by A, right? And plus minus, right? PE multiplied by Y, or multiplied by distance X divided by I. Okay. So for this case, right, this is due to what we call axial loading. Now this we are focusing at point C, okay? And the next component, this is due to bending moment. Okay. And the X, it depends if you want to find about alpha, point alpha, or C that's alpha, and point beta. If you want to find point beta, this is your distance X. Okay, so that is your distance. So now this is for bending. Okay, this is for bending. So by looking at this concept now, okay, and what I'm trying to explain to you is what does it mean by eccentric. Okay, for eccentric, there is this component. Okay, eccentric loading has a what? P over A component. Later on, probably next week, we'll do bending. Okay, you will see this point better. Okay, but now I want to focus on buckling. Okay, now this is bending. Now, if we are going to look at buckling, okay, if we're going to look at buckling, then how do we relate this? Okay, how do we relate this? Okay, so if we look at eccentric, but before we go, well, okay, I'm going to look at eccentric buckling. Okay, we are going now going to look into eccentric buckling. So I'm going to draw two. Okay, I'm going to change. Yeah, I want you to see the difference. Yeah, we have two things side by side. The green is our geometric centroid. Right? And they do have the same thickness. Or the same, yeah, thickness. Okay, now I'm going to call a certain point. Okay. This is my point Q. Okay, our point Q. So again, I'm going to call this my Y. And this is my X. Okay. The column on the left-hand side, the load is applied on the geometric centroid. Okay. So for this case, it is known as centric buckling. right? The one on the right, the force, so this is P, this is also P. The one on the right, P, is not applied at the what? On the green line, right? And it has a certain offset distance relative to the centroid. Okay, so this is a centroid. And it's what we call P. Okay. So now that it is different. Okay. So for this term, this is what we call eccentric buckling. Now, how does this affect our what we learned before? Same thing. Okay, based on bending. So this is not buckling, this is bending. This is our centroid. The force, right, is applied a certain distance away from the what? From the centroid. Okay. So now, if we were to focus on eccentric buckling, right? If we were to focus on eccentric buckling. So when this is a case, if there's an offset, right? If there's an offset, okay. So now we are going to focus on eccentric buckling, okay. So now if there's an offset, right, of E, right? So E is known as our offset distance, right? So because of this offset, there is a moment already, okay. So now we have a moment, and I'm going to call this point A and point B, right? Now there's a moment. So when that's the case, right? So moment at point A is equal to P multiplied by E. Okay. Now this term over here happens before buckling. Okay, before buckling. Now, if you look at centric buckling, right? Before buckling, there is no what? There is no moment. Whereas in eccentric buckling, right? When before buckling, right? There is already P multiplied by E already. Okay, you can see the difference. Okay. Now I'm going to so question for any of you. In centric buckling, when will we have a bending moment for centric? Okay. So I'll write down here no for this case, no deformation. Okay. Right? For this case, no deformation. Right? So for centric buckling, when do we see a moment? Anyone? You can type down the chat and see is anyone typing down on the chat. Maybe the answer is in the chat. Nothing yet. Yes. Okay. So now I'm going to draw centric buckling. And then I'm also going to draw eccentric buckling.